recording? We are recording. So chapter 20, let's do some problems. We'll start with problem number 15. So 15 was asking about finding a resistance, finding a velocity, a drift velocity. So they didn't give you much information, but they did say to use example 20.3. So you go to example 20.3 to figure out how to actually solve this one going forward. Let me pause. So picking up right in the middle of writing stuff. There's the drift velocity equation and then the current that we were given. N. What does N represent?
Time coefficient.
N is not a time coefficient. It's the free charge density. So it's the number of electrons that are free per atom inside of your whatever kind of wire you have. Whatever your wire's made out of. What is our wire made out of? In this problem, it's made out of copper. So we need to know the free electron density of copper. Anybody know that off the top of your heads?
Nope.
Oh yeah, sure, everybody knows this. If you go look at example 20.3, they tell you what the free electron density of copper is. There's one free electron per atom, so you kind of need to do a little conversion. So the conversion that we have here is one free electron per atom of copper, and we need to multiply this by the number of atoms of copper that we have. They give us the density of copper. The density of copper they give us is 8.8 times 10 to the third kilograms per cubic meter. Hard thing about this problem is using something called Avogadro's number. Have you ever learned about Avogadro's number? Where do you learn about that? Chemistry. So physics is taking all the stuff that you learned in chemistry and you're having to apply that here now. Completely out of context.
Would you be giving us that in the test? Would you be giving us this N?
Give you Avogadro's number?
No, give us N. Or would you make us solve for it?
Might make you solve for it. Okay. So we need to actually convert this kilogram number into atoms so that we can get rid of atoms and get just the free electrons. That's what N is equal to. So we take the number of free electrons divided by the number of atoms, multiply that by the number of atoms, and we get the number of free electrons. So we're trying to get that number. Based on this density of copper, we can figure out how much copper we actually have and figure out how many atoms to fill in that density. That's what we're trying to do. So how do we do that? Oh. So we take this free electrons per atom, take this density, we need to get rid of this kilograms. So we can use Avogadro's number. Avogadro's number gives you the number of atoms per mole. So we have 6.02 times 10 to the 23rd atoms in a mole. So again, N, let's be explicit about this. The units of N are electrons per cubic meter. It's the electron density. So that's what we need to get into this. So I have all the units I want. I have electrons and I have cubic meters. But then I have all these extra units coming around too, right? I still have atoms, I have kilograms, I have atoms here, I have moles. Can I cancel any units out at this point? I have atom on the bottom, atom on the top. So I've gotten rid of atoms. What else do I need to get rid of? I need to get rid of kilograms. Okay. Well, I can turn kilograms into grams. 1 kilogram is 1,000 grams. So I got rid of kilograms, but by getting rid of kilograms, I ended up with grams. How does that help me? What else do I need to get rid of? Mark? You just said it. I have to get rid of moles. And in this problem, they give us the molar density of copper. So they give us how much copper, how many grams of copper equal 1 mole. They tell us that 1 mole of copper is equal to 63 grams. So then my moles will cancel out, and my grams will cancel out. And what am I left with? Free electrons per cubic meter. So N, which is the hardest thing to calculate in this problem, is 8.34 times 10 to the 28th electrons per cubic meter. So if I were to give you this on an exam, what kinds of numbers would I give you? I would give you the density of whatever your material is. I would give you Avogadro's number. I would probably give you how many grams are in 1 mole of the object. So I would give you all of these. So this is just a conversion problem. When did we do conversion problems in Physics 1? It was like the first chapter. So this is testing if you can do Physics 1. Applying the same concept, just to different kinds of units. 6.02 times 10 to the 23rd. Okay. Yeah.
So you would always want N to be the electron over the
Yeah.
always.
Yeah.
So if I did like the number that they originally gave us and put it in, it would not be correct.
Right. Right. Okay. So I have N now. I have I have N. Q is the charge. So this is actually something that, oh gosh, what was it? Majestic over there?
Oh, yeah.
Majestic asked about on the quiz. Q. What is Q? Why is it negative 1.6? That's the charge of an electron, because that's what flows. In electricity, the only charges that actually move are electrons. This is something that's very weird about electricity. Current, we define current to be the direction that positive charges flow. Positive charges don't move. The thing that moves is actually the electrons. So whatever direction the current is going is actually the opposite direction of where the charges are actually moving. It's very strange. What are the units on that? Charge, coulombs. And then we need area. So area is the cross section of the wire that we're passing through, and they told us that the radius of this wire is 2.053 times 10 to the negative 3. So this was a given. Cross section area is the area of a circle. Area of a circle is pi r squared. That'd be pi times this radius of 2.053 times 10 to the negative 3. Which gives us an area of 1.324 times 10 to the negative 5. I hear whispering. Are there questions? Yeah. How did what? How did I get Q? So Q is the charges that are flowing down the wire, and the only charges that flow are electrons. If there's something flowing down a wire, it's the charge of an electron. Yeah. Okay.
Doesn't the problem say to double the diameter of problem 20.3?
It says that the diameter becomes double this number, right? So if the diameter is double this, what's the radius?
Oh, radius.
Yeah, because it's pi r squared.
Oh.
So then the number that they gave you
Yeah.
becomes the radius, because they said the diameter is double the radius. So
Yeah.
very sneaky the way they get that to you. When I did it, I originally did say, oh, the diameter is double this, let me take half of this, that must be the radius, but no, I misread it, so. Now I just take all these numbers and I plug them all in. All these numbers go into my drift velocity equation, and I got the drift velocity as negative 1.1 times 10 to the negative 4 meters per second. So that's how fast electrons drift down this wire. Are electrons moving very quickly down this wire then? Is that a big speed? Negative 1.1 times 10 to the negative 4 meters per second. Is that fast? That's really slow. Does that make sense? Electrons are moving really, really slow. Electrons down a wire. How do we know that that doesn't make sense? Where do I see electrons flowing? If I turn off the light. So if I turn off the light, I just shut off all the electrons. If I turn on the light, then I'm going to let electrons start flowing again. So if they're flowing this slow, shouldn't it take a really long time for them to get from here to the light? Doesn't take them a really long time? It basically turns on instantly. Why is that? This is something that's very neat about this drift velocity. The individual electrons move really, really slow, but there's a whole bunch of them. So the electron that's right here, it might move really, really slowly, but it moves very, very slowly because it bumps into an electron that's right next to it, and then that electron bumps right into the electron that's next to it. So even though they're moving slow, the information moves really, really fast because it doesn't have to travel very far. Okay? So that's drift velocity, problem number 15. Any other questions on that one? No? Okay, let's do problem number 37. Problem 37 is all about resistance. And it's relevant to things you might use, tools that you might use. We have digital medical thermometers that determine temperature by measuring the resistance of a semiconductor device called a thermistor, which has this letter alpha equal to negative 0.06 per degree C. So let's write down the number that they gave us. Alpha equals negative 0.06 per degree Celsius, when it is at the same temperature as the patient. What is a patient's temperature if the thermistor's resistance at that temperature is 82% of its value at 37 degrees C, which is the normal body temperature? This is a tricky one. We first have to figure out what equation to use. Well, we know how resistance depends on temperature. Resistance will equal some reference resistance, R naught, times 1 plus alpha times change in temperature. And just to make these consistent, I'm going to call this R2. So this is the resistance at temperature 2. This is the resistance at some reference temperature, T0, and then we have alpha. What numbers do I know? What do I know here? What can I plug in? Do I know any of these? I know alpha. What is alpha? Minus 0.06. What else do I know? I know one of the temperatures. Which temperature do I know? I know the body temperature, some initial temperature. What is that? What is normal body temperature? 37 degrees C. Okay. What else do I know anything else? Do I know RO? Do they give us a value for that? RO equals RO. Do I know anything about R2? 82% of what? 82% of the initial resistance. So it's 82% of the resistance at 37 degrees. So this R2 is 0.87, 87% of R0. Is it 82% or what was it? 32. It's 82%. I just wrote the number wrong.
Okay.
82% of R0. I think that's the hardest part of this one, to realize 82% of the initial resistance is 0.82 times R0. Now I can take all these things and let me plug all these into my equation. So for R2, I'm going to plug in 0.82 times R0. And for R0, I'm going to plug in R0. Then I'm going to multiply by 1 plus negative 0.06 times T2, the temperature of the patient, minus T0, which is 37, the temperature that the patient should be if they're healthy. So what we're doing right now is we're calculating the temperature of everybody that's missing from team 2. Team 2 is missing. Mariah's not here. She's not so mighty, is she? She's sick. You can tell her that next class. Okay, can I solve this? How many unknowns are inside of there? I see 2 unknowns. I don't know R0, and I don't know T2. So how many equations do I need? 2 equations. Can I simplify this at all? I have an R0 here, and I have R0 times all of this. Can't I cancel out? If I divide both sides by R0, I can get rid of R0. R0 goes away. Sneaky, sneaky. That's every teacher's favorite sound. I can cancel that out. Oh! If you were cartoons, I'd see little light bulbs. Okay, so this is 0.82 equals 1 plus negative 0.06 times T2 minus 37. Where do I go from here? Subtract 1 from both sides. What's 0.82 minus 1? Negative 0.18. And that equals negative 0.06 times T2 minus 37. Where do I go from here? Divide by 0.06. What's negative 0.18 divided by 0.06? 3 equals T2 minus 37. So what is T2? 40 degrees Celsius. Is your patient sick? Yes? Is that a fever? Do we know if that's a fever? We're stupid Americans. We don't use the Celsius system. What system do we use?
Fahrenheit.
Fahrenheit. What is their temperature in Fahrenheit? Right? The temperature inside a normal mouth was 90. What's normal temperature? 98.6. Temperature inside a Winterfresh mouth is much, much cooler. You remember those commercials? It just drilled into my head. So what is 40 degrees C in Fahrenheit? What is 40 degrees C in Fahrenheit?
It's like 107. 107.
What is 40 degrees C in Fahrenheit? It's 104? 104. Is this person sick?
Yes.
Should they go to the hospital?
Yes.
Are we glad that Mariah did not come with her temperature of 104 degrees?
Yes.
I certainly am. Send her some soup. And maybe an undertaker. Any questions on that one? We're good on that one? All right, let's do number 51. We're going to calculate how much energy, how expensive it is for you to make avocado toast. With the 1200 watt toaster, how much electrical energy is needed to make a slice of toast if the cooking time is equal to 1 minute at a total cost of 9 cents per kilowatt hour? Okay, so how much energy are you using and how much does it cost in power if you're spending 9 cents per kilowatt hour? So they tell you first that the toaster has a power of 1200 watts. So what variable is that? P equals 1200 watts. How do I get energy out of power? What is the definition of power? Well, what is a watt? This is physics 1. What is a watt? Joule per second. So power is equal to energy divided by time, right? If I want to know the energy that it takes to make this thing, and I know the power, can I solve this equation for energy? Yeah, how do I solve it for energy? Just move the time over, right? Multiply the time over, so energy equals power times time. So the energy that it takes is the power of 1200 watts. Oh, I really hope they gave us a time. Did they give us a time? Yeah, what's the time? 1 minute. So I need to multiply that by 60 seconds. So the energy I'm using, 1200 times 60, I'm using 7.2 times 10 to the 4 joules. Maybe that makes you rethink making your toast. Seems like a lot of energy, doesn't it? 7.2 times 10 to the 4. Is that a lot of energy? No? Let's calculate how much it costs. Let's calculate how much it costs. They tell us, what do they tell us? They tell us that it costs 9 cents per kilowatt hour. So we can do some simple kind of math. Kilowatt hour. I need to take the wattage that I'm using and turn it into kilowatt hours. I need to take that power and figure out how many kilowatt hours that is. Can I do that? Right, because if I take this number and I multiply it by kilowatt hours, then I get out the number of cents. So my power here, power is 1200 watts. Can I convert that into kilowatts? How do I convert that to kilowatts? Divide by 1,000. So it's 1.2 kilowatts. How long am I cooking this toast? 1 minute, 60 seconds. So 1 minute. Do I want units of minutes? I want hours. So how do I get hours out of this? 1 hour is 60 minutes. So I take my 1 minute divided by 1 hour divided by 60 minutes. I get 0.017 hours. So now I can figure out the kilowatt hours that I'm using in making this toast. It's 1.2 kilowatts multiplied by 0.017 hours. This gives me 0.02 kilowatt hours. That is the power times the time to make my piece of toast. I take that number and I multiply it by 9 cents per kilowatt hour. So I'm doing this entirely with dimensional analysis. I'm looking at the units and seeing what I need to get. I take 9 cents divided by kilowatt hour. I multiply it by kilowatt hours. What happens to the kilowatt hours?
Cancel.
Cancels out, and what am I left with?
Cents.
Cents. So if I multiply these together, this gives me the number of cents that this is going to cost. Kilowatt hours cancel out. Is it expensive for me to make my toast?
No.
How expensive is it? 0.18 cents. And actually, technically, that should be 0.18 cent. Because that's not 18 cents. That's 0.18 of a cent. Well done. Did you recently have children? Yeah, because that is totally a dad joke. So is that. I think it was illegal for me to ask you that. I think it was. Yeah, it's on video though. Yeah.
Mine's done it already.
YouTube's gonna turn me in. Any questions on that one? No? All right, let's do the number 55. You asked about 55. Problem 55. This is a cauterizer used to stop bleeding in surgery, puts out 2.0 milliamps at 15 kilovolts. Part A, what is its power output? Part B, what is the resistance of the path? So do you know what a cauterizer is? What is that? It burns. So when you have lots and lots of bleeding in surgery, to stop the bleeding, you literally burn the skin together so that the blood can't get out. Yeah. Let's weld the skin together. That seem fun? No. Hopefully your patient is under anesthesia at the time. So we have a current that we apply from this cauterizer. Current is 2 milliamps. What's probably a good idea to do with this milliamps? Convert it to amps. So milli is 10 to the negative 3. So this would be 2 times 10 to the negative 3 amps. They tell us the voltage of this is 15 kilovolts. So 15 times 10 to the third volts. They want to know the power of this. How do I get power from current and voltage?
Power times I times V.
P equals IV. PIV. P equals 2 times 10 to the negative 3 amps times 15 times 10 to the third volts. So the power that we're using here is 30 watts. Part 2 wants to know what's the resistance of this. How do I get resistance from V and I? R equals V divided by I. What law is this? This is Ohm's law. So we just use Ohm's law. V is equal to 15 times 10 to the third volts. I is still 2 times 10 to the negative 3 amps. So R, the resistance, is 7.5 times 10 to the positive 6 monks. Only got that one. It takes a while. It takes a second. 7.5 times 10 to the 6 ohms. So that's the resistance. Not the people that hate the current government. Resistance. Yeah. I'm trying. I'm tossing and lobbing them out there. See what sticks. Okay, number 88. This is the last one we're going to do. Number 88. So this is, we have a person taking a bath and they wisely touch the metal case of a radio. Is this a smart person? Genius. The pass through the person to the drain pipe and ground has a resistance of 4,000 ohms. So resistance here is 4,000. What is the smallest voltage on the case of the radio that could cause ventricular fibrillation? What is ventricular fibrillation?
Is your heart beating too fast?
It's like your regular
Electrical pattern in your heart gets irregular. Instead of beating, it starts quivering.
Yeah, and then you go into like
MI, and what's MI? Yeah. Lead to cardiac arrest. And what's cardiac arrest? Heart's gonna stop. Heart attack. And you might die. Told you my brother had a heart attack, right? No? Yeah, he had a heart attack when he was 34. He had to have a quintuple bypass. Yeah, so when people ask why I bike, that's why. That gets my heart to be normal heart. If I had a healthy heart to begin with, if I had good genetics, I'd be a freaking Olympian. So unfair. Unfair. But such is life. So we want to know when we have ventricular fibrillation. Ventricular fibrillation happens when you apply current equal to, let me see, it's 100 milliamps to the heart. Can cause ventricular fibrillation. So that is 100 times 10 to the negative 3 amps. They want to know what voltage is necessary. So how many volts do I have to be putting into this toaster to cause ventricular fibrillation in the heart? Or this radio, it's not a toaster. On your exam, it'll be a toaster. I'll be making avocado toast in the bath. Okay, so what voltage? How do I find the voltage here?
V equals IR.
V equals IR. Just multiply it. V equals 100 times 10 to the negative 3 amps times 4,000 ohms. That gives me a voltage of 400 volts. So those were all the questions that I saw submitted as of yesterday when I wrote the lecture. If there was anything that came in after that, or if I missed something, let me know. 92.
There's a 92. How many questions are there?
A heart defibrillator passes 10 amps. I equals 10. Through a patient's torso for 5 milliseconds. In an attempt to restore normal beating. So we're trying to start a person's heart up again. How much charge passed is part A. So find Q. Part B is what voltage was applied if 500 joules of energy was dissipated. So energy, find P if E equals 500 joules. Part C, what was the path's resistance? And part D is find the temperature increase caused into 8 kilograms of affected tissue. All right, this is a test of if I can do physics, because I have not looked at this problem in years. Okay, first I have to find charge. What am I given?
Time.
I'm given current and I'm given time. What is the definition of current? Charge divided by
Time.
time. So charge is the current multiplied by the time. So this charge should be equal to 10 amps times 5 times 10 to the negative 3. So what is this? What's 10 times 5 times 10 to the negative 3? 5 times 10 to the negative 2 coulombs. There's my charge. Okay. Part B. What's part B? Find the power if E is equal to 500 joules. How do I find power?
Energy over time.
Power is energy over time. So that's 500 divided by 5 times 10 to the negative 3. What do I get for the power? 1 times 10 to the 5. What are the units? Watts. Part C, resistance. How do I find resistance? Do I have the V? Do I have V?
No.
I don't have V.
Part B was asking for voltage. It's like what voltage was the 500 joules of energy was dissipated.
Did I read it wrong?
Power.
Low voltage.
Yeah. So
What voltage? Oh, I read it wrong. What voltage? So how do I find the voltage?
power divided by current. Power divided by current.
P equals IV. So V would be P over I, which would be 1 times 10 to the 5th over the current. What was the current? 10? 10 amps. So the voltage would be 1 times 10 to the 4th volts. So part B would be finding the power first and then finding the voltage. Yep. Then part C, sorry, R, V equals IR. So R is V over I, which would be 1 times 10 to the 4th divided by 10. So resistance is 1 times 10 to the 3rd ohms. And then the change in temperature. Okay, for this one, I actually have to scroll back a little bit. I have to look at some equations. I don't remember this equation off the top of my head.
Soccer one.
Yeah.
Resistance changes with temperature. Okay. Part D, let's see how much time we have left. You have 10 minutes left in class. I will find the answer, find out how to remind myself how to do this. I won't ask this on an exam. since I don't know it off the top of my head, you don't have to know it. That's how I pick things.